Hi, this is the video for section 9.2 about estimating a population mean. We talked about point estimates for proportions. Now we want to talk about point estimates for population means. And again, what comes from our sample data is going to give us the best point estimate for our population mean. So the sample mean, x bar, is the best point estimate of the population mean, mu. Here's an example. Pennies minted after 1982 were made from 97.5% zinc and 2.5% copper. A sample of 51 pennies minted after 1982 has a sample mean weight of 2.464 grams. Find a point estimate for the mean weight of pennies minted after 1982. So here, what we're being asked to find is a point estimate for the population mean of the weight of pennies minted after 1982. And again, the best point estimate for that population mean is going to be the sample mean from our sample of 51 pennies. So the best point estimate for the population mean weight is going to be 2.464 grams, which was our sample mean. So first we need to talk about requirements for estimating a population mean. First, the sample is a simple random sample. Second, the sample size needs to be small relative to the population size. So if we have a finite population, then our sample size needs to be less than or equal to 5% of that population size. Third, the data come from a population that is normally distributed, or the sample size is greater than 30. So it has to be one or the other of these two requirements. Either the population was normally distributed in the first place, or if not, or if we don't know about the distribution of the population, then the sample size needs to be greater than 30. Under these conditions, the distribution of this value is a student t distribution for all samples of size n. This is often referred to as a t distribution, and it's used to find critical values, which we denote by t of alpha over 2. The difference between what we're doing here and what we've done before is that we're using a slightly different distribution. Instead of using z-scores from the standard normal distribution, we're using t-scores that come from the t-distribution. So the t-distribution has some specific characteristics. It's similar to the standard normal distribution, so it's symmetric and bell-shaped with the center of the distribution at 0. Just like the standard normal distribution. The t-distribution has more dispersion than the normal distribution and has different shapes for different values of n. A normal distribution is shaped differently depending on the mean and the standard deviation. The t-distribution is always going to be centered at 0, and the shape of the t-distribution depends on the value of n. But as the sample size n increases, the density curve for t gets closer to the standard normal density curve. In other words, for bigger sample sizes, the t distribution looks more and more like the standard normal distribution. So here's a picture of a couple of t distributions for different sample sizes. This one on the very top is the standard normal distribution. The one on the bottom here is a t-distribution when n is equal to 5. And the one in the middle is a t-distribution when n is equal to 15. So you can see here that as the n gets bigger, the distribution is getting closer to looking like the standard normal distribution. To construct confidence intervals that estimate a population mean, part of the formula involves finding critical values, but they come from the t-distribution. So the critical values negative t alpha over 2 and t alpha over 2 are used to distinguish between sample means that are likely to occur and those that are unlikely to occur. These values depend on the value of alpha and on the degrees of freedom for the distribution. The degrees of freedom is related to the sample size n, in this section, the degrees of freedom will be just n minus 1. So here's what our t-distribution is going to look like, and this looks just like what we did with the critical values from the standard normal distribution. Again, we're going to take our confidence level and use that to find alpha. Then we're going to split alpha between the two tails of our t-distribution, and then we're going to find our cutoff values, which will be our critical values. And again, since this distribution is symmetric, the easiest thing will be to find the cutoff value on the left, which will be negative t of alpha over 2, and then we'll just take off the negative as it's the positive t of alpha over 2 that we'll use in our formulas. So here's an example of finding a critical value t of alpha over 2. So we're going to find the critical value t alpha over 2 for a 95% confidence level and a sample size of 51. Now what matters for these critical values is both the confidence level and the sample size, because our t-distribution does depend on the value of n. So we have to know both of these details. So first we're going to do just what we did with the critical values from the standard normal distribution, that is to find alpha. So we subtract our confidence level from 100%. This gives us 5% for this one, so that's 0.05. Then we're going to divide alpha by 2, so that gives us 0.025. Then the other thing we need to know is our degrees of freedom. And again, in this section, the degrees of freedom will simply be n minus 1. So here it's going to be 50. Now on your calculator, you most likely have an inverse t function. This is going to be located in the same place as all those other statistical functions that we've been using. So it's the same menu as where we found the binomial PDF and CDF and the normal CDF function and the inverse norm function. And the numbers that you need for this to use this function are the area, and this one works just like the inverse norm function does, and that is that it assumes that you're going from the t-value to the left. So we're going to put in the area on the left in the left tail, and then you have to put in the degrees of freedom. So it would look like this. Do inverse t and then put in 0.025 and the 50, and you should get negative 2.009 if you round to 3 decimal places. So the critical value we will use will be positive 2.009. Some of the older TI-83s don't have this function, so if your calculator doesn't have this function on that distribution list, then you have to use table 6 from the textbook. And the table is fairly simple. It has areas across the top in the columns, and then it has the degrees of freedom going down the side on the left. Now the margin of error, E for a confidence interval estimate of a population mean mu, can be found by multiplying the critical value t alpha over 2 and the standard deviation of the sample means. So this is a lot like what we did for confidence intervals for population proportions. So our margin of error is t alpha over 2 times s divided by the square root of n. And s is going to be our sample standard deviation. N is our sample size. Now again, the center of the confidence interval will be our point estimate, which is the sample mean, x bar, and the distance the interval spreads on each side is e, our margin of error. So the confidence interval will look like this. The lower limit will be the sample mean minus the margin of error. The upper limit will be the sample mean plus the margin of error. Here's an example of constructing a confidence interval. A sample of 51 pennies minted after 1982 has a sample mean weight of 2.464 grams and a sample standard deviation of 0.02 grams. Construct a 95% confidence interval to estimate the mean weight of pennies minted after 1982. So we already went through the steps to find our critical value for this case, but again, this is going to be different for every different sample size. So again, the steps would be to find alpha over 2, and then the degrees of freedom, which is n minus 1. Put that in your calculator or look it up in the table. Our critical value will be 2.009. Our point estimate, which is our sample mean, is 2.464. Our sample standard deviation is 0.02, and our sample size n is 51. So here's what the formula looks like. We have 2.009 times 0.02 divided by the square root of 51, and that gives us a margin of error of 0.006. So for our confidence interval, we're taking our sample mean minus the margin of error and our sample mean plus the margin of error to get our two limits. And this gives us a confidence interval that goes from 2.458 grams to 2.470 grams. The interpretation for this confidence interval is that we are 95% confident, or we can say there's a 95% probability that the true population mean is between 2.458 grams and 2.470 grams. So the sample size required to estimate the population mean mu with a specified margin of error E is given by this formula. We have n equals z alpha over 2 times sigma star divided by E, and that whole quantity is squared. There are a couple of different things about this formula. For one thing, we have the sigma star. That's an estimate for the population standard deviation sigma. Because again, if we haven't yet selected our sample and gotten sample data, then we don't have a sample standard deviation. So this is just estimating the standard deviation however we can. The other thing that's interesting about this formula is that now we're using the standard normal distribution again instead of the t-distribution. Again, this is because without having already selected our sample, we don't know the sample size, which we need in order to use the t-distribution. So if we don't know the sample size, then we default to the standard normal distribution. Okay, so to get our estimate of our standard deviation, we can either use a value of S, which is the sample standard deviation from a prior study, or we can use what's called the range rule of thumb. This rule says that you can approximate the standard deviation by taking the range and dividing by 4. And there are a lot of situations where you can get a pretty good estimate or have a pretty good idea what the range of the data would be. And if you divide that by 4, that at least gives you some kind of estimate for the standard deviation. Okay, let's do an example of this. So back to the pennies. How large a sample would be required to estimate the mean weight of a penny manufactured after 1982 within 0.005 grams with 99% confidence? So what this is asking is what sample size would we have to have a margin of error of no more than 0.005 with a confidence level of 99%. So what we're going to use for this for our standard deviation estimate is the value of S that we had from the previous study in the previous example, which was 0.02 grams. So to use this formula, again, we're going to find a critical value, but this time it's going to be from the standard normal distribution. So our alpha is going to be 0.01. We divide that by 2 to get 0.005. And now we're using the inverse norm function again. So we have 0.005, 0, and 1, and that gives us a critical value of 2.576. Our standard deviation estimate is 0.02, and the margin of error we want is 0.005. Here you kind of have to read this into the problem because it just says within 0.005 grams. It doesn't say specifically that's what the margin of error is going to be, but that's what that means. So if we plug all this into the sample size formula, we get 106.2. Now, just like we did before, for sample size problems, we always have to round up to the next integer. So we would round this up to 107. And that means the minimum sample size we would need to get this margin of error and this level of confidence would be 107. Here's another example. For a particular model of automobile, a compact non-hybrid, a study is to be done on the miles per gallon. If a 97% confidence interval with a margin of error of 0.75 miles per gallon is desired, how many automobiles should be tested? So again, it's asking how many automobiles we want to test, which is asking what our sample size should be. And notice in this one, we don't have any information. We don't have a prior study on the MPG, so we don't have an estimate for the standard deviation. So we have to figure out how to get one. And to do this, we'll have to use an estimate based on the range and use that range rule of thumb that we talked about. So here, if you think about it a little bit, you can make some estimates for the minimum and maximum MPG for a compact car. We could say that the minimum would be 23 and the maximum would be 33. Again, this is just an estimate, but at least you can have some idea of what those minimums and maximums would be. This would give us a range of 10, and then the range rule of thumb says that we can estimate the standard deviation by dividing the range by 4. So the estimate for our standard deviation would be 2.5. Now the critical value from the standard normal distribution for 97% confidence is 2.17. And then again, to get this, you would find alpha, which would be 3%, divide that by 2, which would give you 0.015, and then put this in your inverse norm function in your calculator, which would give you negative 2.17. Now, if we plug all that into our formula here, we end up with 52.3. One thing to notice here that's a little bit different than for our population proportion problems is that our margin of error is going to be just whatever it was given in the problem. We don't have to worry about converting percentages to decimals in this case. So our margin of error might be anything depending on what kind of problem we're talking about. At any rate, we get a value of 52.3 for our sample size. We're going to round that up to 53. So the minimum sample size we would need for this would be 53.